Okay, hello guys. This will be your lecture six, I think. So we're finally getting rid of the 3D coordinate system. So 3D geometry serves as a background of what we're trying to do from now on. So the actual object that we are studying in this course, the calculus course, the functions, right? As you have seen in the single variable case. So first of all, in this new chapter, chapter 14, the first section is to introduce about the functions of several variables, which is the soul and the core object of what we're investigating this semester. Okay, and just for a brief recall, in chapter 14, we'll be introducing the differentiations about function with several variables, and in chapter 15, we'll be introducing integration. And 16 is just a combination of those two sections, of those two chapters. So before everything there, we will have to introduce this object first, which is the functions, right? So let us start doing this. This will be a relatively simple section because you guys are familiar with functions, so I assume that everything here should be quite simple for you guys. But anyway, let us start this. So first of all, let us do some notation definition on the functions. So for a general function, in this case, I did not really specify what the input and output is. It can be either numbers or anything actually. So A and B are two sets. So let's define something quite simple. Say the set of A is the set of names in our class, maybe. The set B can be the dates, and this function can be the birthday. So for example, uh, say we're focusing on the function of, say, Alan, then my date of birth is like September 9th, so you get 9. That'll be one of the um, functions that is defined, right? So basically, a function is just an assignment of the elements in A, in this case, names, to the elements of B, in this case, date, right? So function can be anything you imagine. Just that we're more interested in the case where A and B are numbers. And in our case, A can actually be vectors, R2 or R3, right? Okay, but for a general function, we can define the following notation. What is the domain of F? The domain of F is where F is defined. So that is what you can put inside A, right? And the codomain of F, this is not really important, so I won't recommend you try to understand this. But the codomain of F is just simply something in the output space of F. So for example, if I do a numerical example, this guy, then the output is always real numbers, right? So it is a function taking the real numbers, sending it to the real numbers. So this will be a domain, this will be the codomain. And as you can see, codomain is actually quite flexible, meaning that you can choose anything that contains every possible values of F. The actual important thing is the range here. So what is a range? A range is a subset of B that is defined through this definition. So it is collecting every possible value of F given any value of A. So for instance, what is the range of this function? This function actually gives everything positive, right? Anything positive and in fact, anything non-negative can be achieved by this function. But f of x cannot be negative, right? It is not possible for it to be negative. So the range of f will be actually every positive and zero numbers. So those are the range of f. It is the possible achievable values or elements for f. Okay. So here is a small figure about the function definition. This will be a domain A. This will be the codomain B. And we're actually interested about how f behaves on A, meaning that we're interested about how big and how large is the range of A. Okay. And obviously the range is a small subset of B. So let's give a quick example. So in this case, I choose f of x to be root x. So obviously you cannot define it on the negative numbers, right? So the domain will be every positive and zero numbers. So let us try to recall the definition here of this notation. So if I write a round bracket or a parenthesis, then that AB is defined to be the line interval of x that collects any x between A and B and not equal to A and not equal to B. If I put a square bracket, that means that you are able to be equal to b. And the same thing happens on the right-hand side. And if it happens on both sides, we put two square brackets. So basically, this is just saying that x can be larger or equal to 0 and all the way up to infinity. Okay. And as I mentioned, the range of that square root function can be of any possible number, right? Possible possible non-negative numbers. So for example, if you take this to be 6, you can solve it and you get x equal to 36, right? So it can achieve any non-negative number, meaning that the range of that function is 0 to infinity, containing 0. And we have mentioned this before. The domain, which is what the input can be of this function x squared, is given to be R, which is every possible real number. And the only possible thing that you can achieve is any non-negative real numbers. Okay, now into our case, which is what we're trying to do in this section. So f of x, y, there's two variables, right? So you have two different objects to play with. And I define this thing to be log x minus y plus y squared. So for example, if you want to evaluate f of 2, 1, you simply plug x to be 2 and y to be 1, and you can get corresponding value. Now, what is the domain of this function? So this comes to the interesting part. For us to define what, actually, sorry, I should put long, okay, I should put L in here. It is a more general notice in your textbook. So if I put ln x minus y here, to define an ln function, it has to be defined on the positive line, right? So ln of something, that something has to be positive, right? Strictly positive. It cannot be 0. So to make x minus y to be positive, you have to choose any point where x is larger than y, strictly larger to be precise. And this is okay. You can put any y here, right? So the actual region of f to be defined is on this region. If you draw this line, this is y equals x. Then anything below here, which means x larger than y, can be defined in this function. And for example, if you do it here, this is say minus 1, 1. You cannot plug this thing into this function because minus 1 of ln is not really defined. Okay. So the domain of this function, which is where it is defined, is given to be this set. So let me emphasize on this in case you do not know. This notation means that we're collecting the elements that looks like this, which satisfies this condition. So in this case, I'm collecting the point x and y in the two-dimensional space such that x is larger than y, which looks like this. This is the thing that we're collecting. Okay. So obviously that set is contained. So again, let me introduce this notation. This is defined. This is contained, meaning that you're dealing with a subset of a larger set R2. So this is a small subset of R2 that is the domain of this function where it is defined basically. Okay, now the interesting about this function is that it is a little bit hard to find out the actual range of this function. Basically, you can in some sense you can see that it's actually R, but let's not focus on that. The point is that it is in general really difficult to find the range of a function, and that is exactly what we're going to do in this chapter. So to find the range of a function, one thing you can do is to analyze its maximum and its minimum, which you guys have already learned in a single variable function, a single variable calculus. But things becomes a little bit delicate when you're dealing with multi-dimensional functions, which in a sense that it'll be a little bit harder to determine whether a maximum and a minimum are. And we'll be covering that in, I think, section 7 and 8. So let's do that afterwards. So we will find the range afterwards, okay? And as I mentioned, codomain is just something that on a plain sight, you know that the value of that function lies in. So in this case, it is R because this is always a real number, right? Okay, so now for the fourth example, I'm trying to write this kind of complicated example. You have three variables, right? So domain will be belongs to R3. There is three different variables. And I define this thing. You have two components of this function. So the first coordinate is x, this string thingy, ex plus square root of y squared minus z plus xyz. And the second coordinate x plus y. So it basically sends a three-dimensional coordinate to a two-dimensional coordinate, right? So on the plane side, we know that it always sends things to R2. Again, we don't know the range. We don't know what is the maximum possibility, if that is something to say, of this two coordinate system. So again, oh, sorry, and I'm circling the wrong thing. Again, let's investigate the domain. So domain is where this function is defined. This guy is cool. It's defined through any x, y, and z. This guy is also cool. This guy is also cool. The only thing that is possible a breakdown is the square root thing. So to define a square root, you have to have the interior argument to be non-negative, right? So we have to have y squared minus z larger or equal to 0, meaning that we're collecting every point such that oh, y squared is larger or equal to z, right? If you draw the picture, it will look like you're cutting some sort of um, parabol parabolic cylinder, and you want to cut that thing out of the three-dimensional space. But basically, it is a little bit hard to visualize. So I will just mention here that we're trying to find a domain, which is where f is defined, and that is all the points, so that y squared is larger or equal to z. Okay. And in particular, this is called a vector value function because it actually gives us a vector. This is the x coordinate and this is the y coordinate. It is actually a function that sends a three-dimensional thing into a two-dimensional object. We won't be investigating this kind of vector value function a lot. It will be deal with a little bit in chapter 16, but for now, let us just consider functions. It is the most important thing for us to consider in this chapter. Okay, I hope you guys are good with those examples. Now, let us give more definitions. So this section will just be about definitions and try to understand those definitions. So the graph of a function, in this case, I also use a general notation, A and B. It's basically collecting the possible values A. Yeah, sorry, A and f of A with the condition that A is belongs to A. So we're collecting all possible values of A, putting it in the first coordinate, and all possible values of f of A, putting in the second coordinate, and that'll be our graph. So that corresponds to our usual understanding of the graph of a single variable function. Say we're dealing with f of x to be x squared, then we're just collecting every a and f of a on the plane, right? So it looks like a parabola in this case. This is a f of a, right? So if we're dealing with a two-dimensional function, then the point is on a two-dimensional space, right? And you have a value in the z coordinate. So that gives you a three-dimensional point, which means that we have to draw the figure in the three-dimensional space. So we see that given x, given x, and given y, you have a point xy, and finding the height as the function value f of xy, you find the point. Connecting those points, you get this parabolic thing. Okay. Well, actually, not parabolic, it is hyperbolic, but anyway, it looks like this. So just recalling back, the definition of a graph is basically collecting every input together with its output, right? So usually what we want to do is to visualize the single variable function and a double variable function because triple variable functions, the point is already lying in 3D space, and there's another value term. So that means that you're actually dealing with a four-dimensional space, which is not really practical to realize and visualize. So this is the most crucial example that we will be dealing with. For a three-variable or multi-variable function, you will just have to sort of imagine how it looks like. Okay, now in general, it'll be very hard to picture a graph of a function. So the idea that we're trying to use here is the level set. So level set basically plays the role that we are projecting our graph onto some lower dimensional space. That is, let me try to emphasize how that works. So, oh, my bad. Here should be. Okay. So for any function, note that I changed the codomain to R, so it is actually a number function. It gives us numbers, not things like date or name or something. So we define a level set of f at the point k. K is an arbitrary number. It can be 1 or 2 or minus 1 or minus 1,000. The level set of this function at k is defined to be this collection. So we're collecting every possible input variables so that the output of that variable will be k. Okay, so let's just see some examples. So for example, let us consider this example two-dimensional function. So what happens if this is equal to 1? This is an ellipse, right? It looks like this. What happens if this looks like 9/4? It also looks like an ellipse, and so on and so forth. So these yellow lines, actually orange lines, are the level set of f at 1, at 9/4, at 4, and so on and so forth. Okay. So you can think of this as like a I'm not sure the English term about that. It's like a mountain, right? You have a mountain, and you're drawing each contour that represents the height of that mountain. So in this case, this is much higher when you're going outward, so it looks like a valley like that. And you can do that for every type of function. For example, if we find f of xy equals to this strange function, x plus sine of xy, then you get this strange level curve, level set, sorry. K equals to 1, 2, 3, and 0. So the level set in this case, when the domain is a two-variable function, then it looks like a curve, right? You can just sort of think of this in a sense that we're having two variables, right? And we're fixing that to be a value. So that fixing make the dimension decrease by 1. So originally you have 2 dimension, but now you fixed some value, so you degenerate you make the coordinate degenerate, and there is only remaining one variable, one dimensional thingy. So the level set in this case usually looks like a curve. And how is that useful? So we can actually utilize that kind of technique to draw a picture, to draw a graph. So you see that, as I mentioned, if I draw this thing on the xy plane, there's different level sets, then the more closer to the origin the level set will be, the less of the value, right? For example, this might be 1, this might be k equal to 2, this might be 3. And if I do that projection onto the z coordinate, you get, for example, if this is 1, then height will be 1 here. If this is 2, then height will be 2 here, and so on and so forth. So by visualizing the level set on the two-dimensional plane, you can sort of figure out what it looks like in what the graph looks like in the 3D space. So this is another complicated example. We have drew every kind of level set here, level curve. So you have the red thing, you have the blue thing. I think this corresponds to 1, 2, and 3 or something like that. And again, this is 1, right? So you lift it up by 1 unit. You lift this blue line up by 2 units, and so on and so forth. And then you get this strange kind of graph thingy. So basically level set, or in more particular level curve, is just finding some particular curve that represents the height of the function. And by connecting those heights, you will get the graph of the function. It's a way to understand the graph of the function through a low dimensional projection. Okay. So yeah, lastly, let us give some nice examples. There's not really much exercise to do in this section. It is basically an introduction on how function works in multi-dimensional variables, but every function actually works the same. We will be investigating more on the difference about multi and single variable functions in the next sections. Okay. So in this case, actually, I have a remark here. Sorry. So as I mentioned, if we're dealing with a two-variable function, the level set looks like a curve, right? If you're working with a three-variable function, the level set works like a surface. So for example, if we're dealing with the function like x squared plus y squared plus z squared, f of x, y, z, then by setting it to 1, 2, or 3, gives you something like a sphere, right? So the level set will be looking like a sphere, a two-dimensional object. As I mentioned before, by restricting a condition on the value, you are taking out some variable. So a three-variable becomes a two-variable or a two-dimensional thingy. However, I already mentioned that a surface is already very hard to draw in a 3D space. So to sort of picture that 3D space as a projection in a 4D space is actually much harder. So in most cases, when we're asked to draw about some function, it'll be mostly about the variable function. And we can draw that by projecting the level sets on 2D plane, which gives us a one-dimensional level curve, and we can draw the height back and into a graph, right? And I would say that it is not really important nowadays to understand a function in its graph because basically you can draw everything on like decimals or GeoGebra, right? So this won't be a very crucial point. The crucial thing is about how to understand the maximal and the minimal value of a function, which we will um, investigate later on. So to end this section, let us try to do some example in the textbook. So f of x y given to be this 1 plus root of 4 minus y squared. We have three different problems. So let's do that individually. So first one is 3, 1. You basically plug x to be 3 and y to be 1. In particular, in this case, it does not really depend on x. So you just plug y to be 1, which you get 1 plus root 3. And to sketch a domain of f, recall that the domain of f is where it is defined, right? So it will be some subset of the two-dimensional plane. Now, what is the restriction on this function? The only possible restriction is this square root. Y squared have to be less or equal to 4, right? So the only requirement is y squared less or equal to 4, meaning that y have to be between plus 2 and minus 2. So you have this kind of graph. So note that I want to emphasize here that I include the line here, so I make it solid. In the previous example, where I say the logarithm here have to satisfy x larger than y strictly, right? So I put a dot line here. So note that the difference, this set does not contain a line, and this set does contain a line. I will use the difference between dotted line and solid line to present this fact. Okay, lastly, we want to find the range of f, which is the maximal and the minimal value for f. And it is quite obvious that this guy is actually less than 2 and larger than 0, right? So the possible value for f will be 1 and 3. And the equality is actually achievable because, for example, if you plug y to be 0, you will get 3. If you plug y to be 0, 2 or minus 2, you will get 1, right? So both of this minimal and maximal value are achievable. You actually have a square bracket, okay? You're not dealing with this guy. You're dealing with this guy. So in this case, it's quite simple to analyze. The minimum value for f is 1. The maximum value for f is 3. So the range of f is just this interval. It can be evaluated in every number within 1 and 3, containing 1 and 3. Okay, so that is all. I don't think we need a review because it is quite a short section, but just be aware that you should know the term like domain, like range, graph, and level set, a level curve to be precise. Okay, so that'll be all on the introduction of function with several variables. I encourage you to try to look into the textbook much on this particular section because there are very many like nice graph about stranding function in 2D space or 3D space in the textbook. So yeah, try to look in the textbook and let me know what you think about it. So I'll be seeing you in our next section, which is the limit and continuity, and that will be the starting point of our calculus. So be prepared. We're going to dive in something quite abstract, and the actual math will start there. See you.